When a production line unexpectedly seizes, academic theory offers very little comfort to the floor manager staring at a dead machine. Most practitioners know the macro philosophies. You are likely familiar with total quality management, Garvin's 8 dimensions of product quality, or the broad phases of the Giron trilogy. But those overarching philosophies do not dictate which specific mathematical model or statistical chart you need to deploy to diagnose a stalled pipeline or a recurring defect. Applying the wrong tool to a specific operational problem creates false confidence. It hides chronic waste in the data and allows minor variances to compound until they result in catastrophic product failures. To bridge the gap between physical defects and business strategy, Dr. Joseph Giron championed the Cost of Quality, or COQ, accounting system. COQ is a framework that translates quality issues into the language of money, allowing management to track the financial impact of poor quality over time. This chart models Giron's approach. Look at the left side, where the cost of poor quality plateaus. This high baseline of inefficiencies, scrap and rework, often becomes accepted as a normal operating expense, which Giron labels chronic waste. When an organization initiates a targeted improvement project, you see a temporary cost spike to solve the problem. Once addressed, the baseline waste drops permanently, settling into a much lower, highly efficient zone of quality control. True mastery of quality management lies in the strategic selection of the exact framework needed to reduce that chronic waste. Simply memorizing definitions will not solve the operational problem. In Six Sigma, the first strategic decision is, are you improving an existing process or creating a new design? For broken legacy processes, use DMAIC: define, measure, analyze, improve, control. It is a cyclical framework used exclusively to root out defects in already operational systems. The operational limitation of DMAIC is that it can only optimize a system up to its original design limits. But if the foundational architecture of the process is fundamentally flawed, no amount of tweaking will ever exceed that ceiling. When you need to build a system from scratch or entirely replace a broken one, you switch to DMAV. DMAV stands for define, measure, analyze, design, and verify. Because there is no existing process to measure, DMAV relies heavily on early-stage predictive metrics and the voice of the customer, or VOC. VOC is a research process used to capture a customer's expectations, preferences, and aversions. This approach comes with a strict operational trade-off. Building predictive quality from the ground up requires massive upfront capital and a significantly slower time to market. Choosing between DMAIC and DMAD forces leadership to decide whether to maximize the efficiency of current constraints or spend heavily to erase those constraints entirely. Down on the factory floor, tracking daily continuous operations relies heavily on a system known as Statistical Process Control, or SPC. SPC is a methodology that uses statistical formulas to monitor, control, and reduce variation in a process. The success of SPC depends entirely on selecting the correct control chart. This choice is dictated by 2 strict conditions: the type of data you are collecting, whether it is continuous or attribute, and the size of your sample. For continuous variables with small samples under 9 units, use an X-bar and R-chart combination. The X-bar chart tracks the process average over time to detect drifting. The R-chart below it measures the range between highest and lowest values, tracking output variation. However, when production scales up and your sample size reaches 10 or greater, the R-chart loses its statistical validity. For these larger datasets, the R-chart must be replaced by an S-chart, creating an X-bar and S-chart combination. The S-chart tracks standard deviation. It provides much higher statistical accuracy for large samples, but requires complex calculations that are significantly harder to execute manually. The rules change completely for the second major data type, discrete attributes. You aren't measuring variables like weight. You are simply counting binary flaws, like a deep surface scratch or a completely missing screw. To track the overall count of nonconformities within a single fixed inspected unit, you use a C-chart. The C-chart is effective for recording the existence of defects, but by only counting attributes, it ignores the underlying continuous variables actually causing those defects. If you misapply these tools, for example, using an R chart to evaluate massive datasets or an X bar chart to count discrete flaws, you generate mathematically invalid control limits. This renders the entire quality tracking effort blind to actual failures. When an SPC chart signals that a process has drifted statistically out of control, operations teams face the immediate dilemma of diagnosing the defect. This is the Ishikawa, or fishbone diagram. It's a qualitative, reactive tool used to brainstorm root causes after an adverse event occurs. It organizes human insights by mapping subcauses into primary categories, known as the 6 M's: machinery, methods, materials, measurement, manpower, and Mother Nature. The operational trade-off of the fishbone is its subjectivity. It relies entirely on the prior knowledge and opinions of the personnel in the room. If the team lacks experience, the diagram will not uncover the true root cause. The counter approach is failure mode effects analysis, or FMEA. FMEA is a highly structured, anticipatory tool used proactively during early design phases to catch vulnerabilities before production begins. FMEA uses historical data to score potential future failures across 3 criteria: the probability of occurrence, severity of the impact, and the likelihood of detection. Implementing FMEA is extremely resource-intensive. It requires vast amounts of accurate historical data to model compliance effectively and demands significant cross-functional engineering time. The Ishikawa diagram is the required tool for fighting daily operational fires on the floor. FMEA is the architectural firewall built to ensure those fires never start in the first place. The true test is matching your process to the correct framework. Line fixers use qualitative Ishikawa diagrams for fast alignment and quantitative X-bar R charts for control. Innovators operate differently, using the DMA-VAV framework and FMEA predictive modeling to build proactive, quantitative safeguards into new designs. Meanwhile, an executive sponsor focuses strictly on macro frameworks like the Giron trilogy. They utilize the cost-quality system to translate technical floor data into the financial terms required by the boardroom. Quality management is a highly specific mathematical toolkit. Deploying a C chart when you need an X bar chart or defaulting to DMAIC when you are designing a new product will actively harm the operation. Knowing the definitions of these concepts merely passes the academic test. Mastering their operational trade-offs and applying the precise tool to the specific friction point is what actually solves the business problem. The ultimate test of a quality practitioner is accurately diagnosing the maturity of their own process and matching it to the correct framework. For an operations fixer managing an active line, the toolset is clear. They rely heavily on the qualitative Ishikawa diagram for fast team alignment and quantitative X-bar and R charts for daily continuous control. An innovator or product designer operates in a different quadrant. They bypass DMAIC entirely, utilizing the DMA-VD framework and rigorous FMEA predictive modeling to build proactive, quantitative safeguards into new designs. Meanwhile, an executive sponsor focuses strictly on frameworks like the Giron trilogy, utilizing the cost of quality system to translate technical floor data into the financial terms required by the boardroom. Quality management is a highly specific mathematical toolkit. Deploying a C chart when you need an X-bar chart or default into BMAIC when you are designing a new product will actively harm the operation. Knowing the definitions of these concepts merely passes the academic test. Mastering their operational trade-offs and applying the precise tool to the specific friction point is what actually solves the business problem.